Welcome to a lesson with Dr. Powell. Let's take a look at an identity for binomial coefficients, which is kind of cool, but look at some examples of it. For instance, if we take 6 choose 3, where this is a double of that one, so 6 choose 3, we can think of this in the following way. We can write out something like this: 3, 3, and think about ways that things add up to 3. We could either have 3, 0, or we could have 2, 1, or we could have 1, 2, or we could have, let's see here, or we can have 0, 3, and those are our options. Now, if we added these together, we'll get this. So it's kind of like if we have a double, then what we do is we can go to this 3, and we can think ways of adding together make 3. So let's do that. 3, 0, 2, 1, 1, 2, 0, 3. So we have all those. And then we just kind of put these into these products right here. We add those together, and it should be equal. You can try it out just to make sure. So 3 choose 3 times 3 choose 0, both of these are 1. So that's just a 1. This right here, both of these are 3. So 3 squared. In fact, notice by symmetry, these two guys are always the same. So even if we wanted to, well, let's just keep going. So this is, okay, so this is 3 squared. This is also 3 squared. And this is 1 again. So we get 1 plus 3 squared plus 3 squared plus 1. So that would be 9 plus 9. So 18 plus 2, so 20. So we should be getting 20 out. Let's see if that's what we get when we do this calculation. Let's think 6 times 5 times 4, 1 times 2 times 3. That computes out to 6 choose 3. And we do get 20. So this is kind of an interesting relationship between a binomial coefficient, where we have a double up here of that, and this product right here. So now another way of thinking about this is by symmetry. We could even just say, this is just this squared. So 3 choose 3 squared. You could do this is 3 choose 2 squared. This is 3 choose 1 squared. This is 3 choose 0 squared. Notice how we just walk through it like that. So we kind of have a fun identity. Maybe we should write down exactly the form that this identity takes. So this is like saying if we have double up here and that, this is the same thing as n choose n squared plus n choose 1 squared plus going down, or n minus 1, sorry, n minus 1. So n minus 1, okay, we're going down like that, n minus 2 squared, and we keep on going down until we end up getting n choose 0 quantity squared. So this is a fun identity, right, that we can use between that relates binomial coefficients. Now, how can we prove this, that this actually always holds true? This can come from using polynomial multiplication. Think of this, for instance. Well, where does this come from? This is a coefficient when you have something raised to the 2n, in fact, like x plus 1, and it'll be the coefficient of x to the n. So when you expand this, that'll be that coefficient right there. Now, over here, maybe we should rewrite this the way that it actually kind of was looking. So more like n choose n and 0, right? Okay, so we can kind of get a feel, because maybe the identity will come from that idea. So we have n choose n minus 1 and n choose 1, right? Plus so forth onward to n choose 0 and choose n. Okay, so it kind of looks like just like we had before, these guys right here always add up to n. And adding is important because that kind of means like exponents adding up to n, like an x to the n minus 1 times times an x to the 1. But maybe we're multiplying two polynomials together such that this would be combined in such a way that these coefficients, that we have some coefficients here with these x's coming from some multiplication where this multiplication of polynomials, so maybe even something like, something like this. So maybe we ended up getting this when we multiplied two polynomials. So it looks like we're just multiplying two polynomials because we have something in one being multiplied to something in the other. And we're looking at an x to the n power, but we have lots of x to the n powers to add up, meaning we have two things we're multiplying together. But see how these groupings are there's just two. So we have two things that we're multiplying together to make to make this polynomial, and we are equating maybe coefficients of x to the n, since this happens to be the coefficient of x to the n over here. So how do we? The question is, what are these two polynomials, and how does that work? Well, we can kind of think about this a little bit. Notice that all of these coefficients are have an n on the top. That means they came from maybe an to the nth power. In fact, even like x plus 1 to the n. Seems reasonable that this would be, because I know that when we multiply this and this together, you actually get that. So this really looks like that should be true. But the question is this really the coefficient of x to the n? Like, well, I know, let's see, when we multiply this out, we got to think about this. When we expand x plus 1 to the n, we're going to have lots of things in there. We're going to have, let's just particularly look at one thing that we might have. One thing that we might have is we might have like x to the n minus 1, because of the nth power, right? So what's the coefficient of that? N choose n minus 1. Okay, so we can, if we pull this from this polynomial, since we're multiplying, it's going to be multiplied to, okay, so this is one of the things in here. It's going to be multiplied to everything over here. Now, what do we multiply it to over here so that we have an x to the n? Because we're going to collect all of our x to the n terms, right? So what do we need to multiply it to it over here? So we have x to the n. Well, let's see. We need to multiply it to an x to the 1, and that coefficient would be n choose 1. Oh my goodness. So if we multiply those two together, that's like this right here, right? That's like the coefficient of x to the n right over here. Oh, from multiplying those two guys to get one of our like terms that we're going to be adding. Now, what about this one? Well, that one would come from maybe an x to the, choosing an x to the n over here, and then choosing a 1 over here, which is the same as this, right? That would be x to the n. Okay. Now we could even choose, okay, what about an n minus 2 and an n2, right? That would be the next guy over. Where would that come from? So let's see, that would come from, well, n choose n minus 2, so a power of x n minus 2. So that would be paired up with to the second power, which would be a 2 here. Oh my goodness, that looks like exactly where it comes from. So in other words, this polynomial multiplication right here actually proves this particular identity. Let's now walk through, with that in mind, walk through symbolically how we might do that. Let's think about x plus 1 to the n times x plus 1 to the n, and let's think about this as a sum. It's a sum like this, nk x to the k goes from 0 to n. This right here, let's use j this time, just so it's different here. We're multiplying these two series together, times that are these two sums together. So here we have n choose j, x to the k, or j, sorry. And then we multiply those together. We're supposed to get x plus 1 to the 2n. Okay, so that's, so n, okay, yes. Okay, so to the 2n, so maybe we'll use a different thing here. It doesn't really matter what we use. We could use a k again. So k goes from 0 to 2n, and we have 2n choose k, and we have x to the k. All right, now we want to equate x to the n terms. So over here, this is a lot of things added together. And the term that we're interested in is the x to the n term. The coefficient is 2n choose n. This coefficient should be the coefficient of x to the n over here when we do this multiplication. Now, when we do this multiplication, we're pairing a term in here with the term in here multiplied, and then we're adding up other ones that are multiplied such that all the ones I add up actually give me x to the n each time, so we can add them to get an x to the n term, so we can equate the coefficients. Now, so what do we add together? Well, let's think about this. We're going to be pairing things. We're going to be pairing something over here with something over here such that k plus j is n. So in other words, we're looking at n, or see here, write that as k plus j equals n. Well, if k plus j is equal to n, we could actually do a couple things. We could rewrite this as x to the k, so x to the k plus j, which we know is n now. So we could just say this is nj, and then we can have x, so then we just have x to the n. And pretty much we can factor the x to the n out of all these terms, out of the whole sum even of these guys. Just factor the xn, so we have the coefficient. Factor the xn out of this one thing, and we have that coefficient. So that means this coefficient is equal to that. Now, so we have this identity, which we can rewrite, we can write in this particular way. Now, by symmetry, since we know if k plus j is equal to n, these two guys are actually the same, we could actually just let k range from 0 up to n, because it can range in that, and in the idea of k plus j is equal to n. So k goes from that, and then we can just square and choose k here. And so then we get that this is equal to this, and that is our identity. Thanks for watching.